At the macroscopic scale, the universe follows predictable mechanical rules. Gravity pulls mass together. Electromagnetism repels or attracts based on charge. At the quantum scale, the strong nuclear force binds quarks together to form protons and neutrons. It operates under rigid constraints, strictly conserving color and electrical charge during every interaction. Gravity, electromagnetism, and the strong nuclear force share an inflexible boundary. They can push, pull, and bind matter together, but they cannot alter a particle's underlying identity. In a universe governed exclusively by these three forces, the elemental composition of matter would be permanently locked. Hydrogen could never fuse into heavier elements, and complex chemistry would never exist. This matrix displays the standard model particles: quarks, leptons, and gauge bosons. Zooming into a neutron, it undergoes beta- decay. A down quark transforms into an up quark, becoming a proton. This unique flavor change ejects an electron and anti-neutrino, balancing the quantum equation. In 1933, Enrico Fermi proposed the first mathematical model of this decay, describing it as a four-fermion contact interaction with zero range. To understand how the cosmos forged heavy elements and why matter dominates antimatter, we must map the mechanics of this flavor-changing engine. Flavor change is the physical result of a specific quantum vertex known as a charged current interaction. This kinematic Feynman diagram maps a down quark transitioning to an up quark over time. To conserve electric charge during the transition, the down quark, which has a charge of -1/3, must emit a virtual W- boson. Looking at the mathematics at the vertex, the ejection of a -1 charge leaves the newly formed up quark with a charge of +2/3. The W- boson is unstable. It propagates briefly before branching off and decaying into an electron and an electron antineutrino. Flavor change is a mathematical transaction of charge, mediated by a specific force-carrying boson. The weak interaction is named for its apparent lack of intensity, yet at distances of 10 to the -18 meters, it rivals the electromagnetic force in field strength. The true limitation of the weak force is carrier mass. While the photon propagates endlessly as a massless ripple, the W and Z bosons are massive, highly localized distortions, weighing roughly 90 giga-electron volts over c². These force-carrying bosons are nearly 100 times more massive than an entire proton. This extreme mass creates a severe kinematic bottleneck, requiring enormous amounts of energy to briefly manifest these heavy particles, restricting their lifespan to less than 10 to the -24 seconds. Because they decay so rapidly, the effective range of the weak force is restricted to a fraction of a single proton's radius. The sluggish decay rates observed in weak interactions are a consequence of these heavy force carriers, making weak decays drastically slower than electromagnetic or strong nuclear processes. The weak interaction is governed by a specific rule set known as weak isospin, designated as T3. Weak isospin operates as an additive quantum number, serving the same gating function for the weak force that electric charge serves for electromagnetism. Looking at this grid of weak isospin values, the standard model fermions are bracketed into left-handed pairs. The up quark and the neutrino hold a value of +1/2, while the down quark and the electron hold a value of -1/2. This dictates a rigid rule. Quarks possessing a T3 of +1/2 can only decay into quarks with a T3 of -1/2. The interaction requires this precise alignment of values to ensure weak isospin is always conserved. In addition to flavor-changing charged currents, the neutral current interaction is instead mediated by the massive Z0 boson. Unlike the W bosons, the Z0 transfers momentum without altering a particle's flavor or its electrical charge. It is responsible for the elastic deflection of neutrinos. Weak isospin provides the invisible tracks for the weak interaction, gating the physical identities that matter is permitted to assume. For decades, physicists assumed the laws of nature were conserved under mirror reflection, a concept called parity symmetry. The weak interaction is the only fundamental force that violates this spatial symmetry. In 1957, Chen Xiang Wu conducted an experiment on cobalt-60 decay that proved this violation, revealing that the universe does not treat left and right identically. This visualization demonstrates particle chirality. A left-handed particle is defined by a spin vector pointing in the opposite direction to its momentum. To account for Wu's findings, physicists developed the V-A Lagrangian. This rule states that the charged-weak interaction exclusively couples to left-handed fermions and right-handed antifermions. Watch the interaction vertex in this diagram. It couples when a left-handed particle approaches, but remains inert as a right-handed particle passes through it. To a W boson, a right-handed electron is invisible. The universe is asymmetrical at its lowest level. The weak force acts as a selective physical filter, discriminating based on geometric handedness. If the electromagnetic and weak forces differ so drastically in carrier mass and parity symmetry, how can they stem from the same origin? In the late 1960s, Sheldon Glashow, Abdus Salam, and Steven Weinberg developed the electroweak unification theory to resolve that question. Their mathematics showed that at the extreme energies of the quark epoch, the weak and electromagnetic forces were a single unified electroweak interaction, mediated by 4 massless bosons. As the universe cooled, this symmetrical state underwent spontaneous symmetry breaking via the Higgs mechanism. In this visualization, 3 of the bosons acquire immense mass, becoming the heavy W and Z bosons, while the photon remains massless. The parity violation of the weak force is also linked to the rarer charge parity violation, mapped mathematically by the CKM matrix. Charge parity violation occurs when particles and their antimatter counterparts behave differently. This provides the loophole for baryogenesis, the reason a surplus of matter survived the early universe instead of perfectly annihilating. Without this asymmetrical flavor-swapping engine, stars could not fuse hydrogen into heavier elements. The stable matter required to build our world would simply not exist.